In this video, you will learn how to answer forces questions when the object is on an inclined plane, like a car driving up a hill or a box that's just sitting on a ramp. And the first thing you have to learn is how to draw a free body diagram for an object that's on an incline. Let's start by looking at what we would do for a flat surface, and we'll use an example. For instance, this box that's sitting on the ground. Now normally I would just draw a point that represents the object, and I would draw the forces that are acting on that object. So in this case, gravity and the normal force. And now normally I don't draw the x or y axis in my free body diagrams, and that's just to save some time. But if we wanted to, we could do that like this. Now let's look at an inclined surface. So for example, we have this box that's sitting on a ramp and the box is not moving, it's just sitting there. If I wanted to draw a free body diagram for this, I would have to rotate my x and y axis to match the incline, and that would look like this. So you can see now the x-axis is along the inclined plane, and the y-axis is tilted accordingly. And so what you have to recognize is that when you're dealing with an inclined surface, this is how you have to draw your x and y axis. And then from there, you can draw your free body diagram. The first force that I will draw is the force of gravity. And now what I hope you notice is that the force of gravity points straight down. And this is how you will always draw the force of gravity, because the force of gravity always points straight down. And now our inclined plane also has an angle. And if we want to represent this angle on our free body diagram, we have to draw it right here. And now what I hope you notice is that because the force of gravity vector is at an angle, we can break the force of gravity into an x and y component. So we have the y component of the force of gravity, Fgy, and we have the x component of the force of gravity, Fgx. Now we also know we have a normal force because the object is on a surface and the surface is pushing back up against it. And the normal force is directly along the y-axis because the normal force has to be perpendicular to the surface. And now based on the free body diagram that you see here, we could see that there would be a net force down the inclined plane. But I said this box is not moving. So what force is preventing the motion of this box down the inclined plane? Well, that would be static friction. So we could draw the static friction force right along the x-axis. And so this was an example of how you can draw a free body diagram for an object that's on an inclined surface. The next thing I want to show you is how you can find the x and y component of the force of gravity. If I take the x and y component and I use vector addition to add them tip to tail, the resultant is the force of gravity vector. And because we have a right angled triangle, we can use trigonometry to solve for Fgy and Fgx. Let's start with sine theta, which we know is equal to the opposite side divided by the hypotenuse. The opposite side is Fgx, and the hypotenuse is Fg. If we rearrange this equation, we see that Fgx is equal to Fg sine theta. But we can expand this even more, because we know the force of gravity is equal to mg. So we can replace Fg with mg, and we see that Fgx, the force of gravity in the x component, is equal to mg sine theta. Now let's solve for Fgy. We will use cos theta, which is equal to the adjacent side divided by the hypotenuse. The adjacent side is Fgy, and the hypotenuse is Fg. When we rearrange this equation and replace Fg with mg, we find that the force of gravity in the y component is equal to mg cos theta. And that is how you find the x and y components of the force of gravity. Now let's do a question to practice what we learned. Here we have a 2,000 kilogram car, which is accelerating at a rate of 2 meters per second squared up a hill with a 30-degree incline. Now we are told that the coefficient of kinetic friction is 0.2, and we want to know what is the thrust force from the car's engine. Now the first thing we want to do is draw a free body diagram. And I always like to draw my tilted axis. Then I draw the force of gravity vector pointed straight down. I put my angle between the force of gravity and the y-axis, I draw the normal force directly along the y-axis. We also have a car with an engine, so I need to draw the thrust force going up the incline, and there will be some kinetic friction between the tires and the surface, so I draw the kinetic friction going down the incline, resisting the motion of the car. And of course, I have to remind myself that we have a y component and an x component of the force of gravity. And remember, the x component, Fgx, is equal to mg sine theta, and the y component, Fgy, is equal to mg cos theta. The next thing you want to do is write your F net equations. And we will start with the F net x equation, which is the sum of all the forces acting along the x-axis. So that would be the thrust force minus the kinetic friction minus the force of gravity in the x component. And the kinetic friction and Fgx are negative because they are vectors that are pointed to the left. We also know that the car is accelerating, so F net x can be replaced with ma, and we can also replace the kinetic friction with mu kn, and we can replace Fgx with mg sine theta. And now I will just rearrange this equation to isolate for the thrust force, because that's what we're solving for. And now looking at this equation, we know the mass of the car, we know the car's acceleration, we know the coefficient of kinetic friction, we know the acceleration due to gravity, and we know the angle of the incline. That means the only unknown is the normal force. And in order to find the normal force, we will need to use the F net y equation, which is the sum of all the forces acting along the y-axis. So that would be the normal force minus the y component of the force of gravity. And Fgy is negative because it's a vector that points down. Now we can replace F net y with 0 because the car is not moving up or down, meaning there's no net force along the y-axis. I can also replace Fgy with mg cos theta, and then all I have to do is rearrange the equation to isolate for the normal force, plug in my values for the mass, the acceleration due to gravity, and the angle, and we find that the normal force is equal to about 16,974 newtons. And with that, I can solve for the thrust force by plugging in all the known values. And what we find is that the thrust force for this car is equal to about 17,195 newtons. And that is how you answer forces questions when the object is on an inclined surface.